Tech Talks. Today we are going to be talking about turbo compressors, and with that is a person here who has a PhD from arguably Switzerland's most renowned technical institution. He currently works at Celeriton. That's the ETH, actually, what I meant. He currently works at Celeriton, where he's heading up the R&D for fuel cell applications, essentially. Welcome, Marcus. Marcus Brandstetter.
Hello, Stephen. Thank you for having me. It's great to be on your show.
Remotely.
Thank you, Marcus. Yeah, you are connected to us by video link, and you are in a special place. Can you tell us a little bit where you are, please?
Yes, I'm currently in one of our main working session rooms, right next to the entire research and development department of our company, where all the concepts or the new concepts that we develop are being brainstormed or are being presented.
Okay. Wonderful. So that is just next to all the R&D guys. I know you head up the team, but the good news is, in case we run into any serious technical question here, you could quickly probably hop over to your colleagues there, right?
Exactly. Then I can grab my specialists and take their meetings.
Super. Okay, so perfect. Let's go right into the topic. Marcus, what is a turbo compressor?
Actually, for that matter,
so it's terribly formulaic, all right?
An image that
what Julian does is he introduces his guest, and then he says, what is a turbo compressor? Well, if you don't really understand why you might need a turbo compressor in a fuel cell system, you shouldn't really be watching this video. And the poor lad now has to go and find a turbo compressor and explain.
I could show you to give you a little bit of an overview of how such a turbo compressor looks like and how it functions.
Okay, yes, we see it.
So you can see it. All right, great. So on the left-hand side, you can see a simplified schematic overview of how such a turbo compressor is built. So fundamentally, it consists of three, or in the simple form, it consists of three parts, which is the impeller, so the wheel that works on the fluid.
Yes.
The diffuser, which is followed by our impeller, and after the diffuser we have a so-called volute or spiral casing, which connects the compressor to the fuel cell stack, for instance.
So the impeller is that's number 2 on that picture. Number 2, and that's
yes,
what's
so impeller is you can see it right here.
Yes.
Diffuser is number 4, and the spiral casing is essentially number 6.
Understood.
Okay, so maybe, and now we can briefly go through step by step.
Yes.
What happens, like from a fluid perspective. So at inlet, which is indicated by number 1. Going essentially the flow is directed towards the eye of the impeller. When it's talking about the eye, which is the center of the impeller. The high rotational speed. Impeller is rotating. We have a so-called flow passage, which is generated by the blades of such an impeller.
Yep.
Where we have essentially an increase or a change in angular momentum of the flow, and a change of total pressure. So across this flow passage, which is created by the spiral casing, which is the outer contour, and the impeller, around 60% of the total pressure increase is taking place.
Okay, so as that spins, that increases the pressure going up. Okay.
Correct. So it's essentially, first of all, it changes the angular momentum and it increases the total pressure.
Okay.
What is interesting to note.
No dimensions. No sense of dimensions at this stage.
After, for instance, at the edge of this impeller, we have still flow velocities of around 200 meters a second. Which means we need to still decelerate this flow to further increase the static pressure that is required for certain applications. This is done by the so-called diffuser, where we increase the volume, thereby increasing the static pressure. After the diffuser, we have, as I said, the so-called spiral casing or volute, where we further reduce the radial velocity and collect the flow towards the end application, which could, for instance, be a fuel cell stack.
Yeah.
And maybe on the right-hand side, you can see one of our more recent designs that we have already presented at numerous fairs, where we can see actually how it looks in real life, which is a cut through of our one of our CAD designs. So maybe I can also show you how typically such like what is the variation of such impeller designs, which is from my perspective very interesting to see. As you can see, there's a huge variety. So-called mixed flow designs, where we have also a radial component, or the classical design, which one would see in fuel cell stack applications.
So what is the difference between one that let's say narrows up and one that's completely what's the main difference?
So the main difference is directed. It's a very technical question actually. The difference is directed to the flow coefficients. So essentially the throughput that such a compressor needs to be able to be designed for. For instance, once we go towards axial flow designs, which is a classic for gas turbine designs, for instance, we have high mass flows requirements. Whereas when we go to really radial designs, which is, for instance, a purely radial design, 2D even, we have very low mass flows.
All right. Okay. So the mass flow essentially makes a difference. Okay.
Correct.
Well, so you have already mentioned some applications. Where do we typically find turbo compressors in the hydrogen economy?
Yes, I mean there are three main applications actually, and also actually for that purpose I also brought you another image that I could show you, which is a very simplified schematic of a proton exchange membrane fuel cell. So piping diagrams essentially, where we can see the air inlet, and here we have our air compressor. It's one of the main application areas for these turbo compressors, compressing the air. Generating for the cathode side to produce the air.
So has he got an operating system within 15 meters of him?
By these fuel cell stacks.
If not, why is he talking?
It pushes the air into the humidifier, and then
why could we not see it operating?
And it needs also cooling, as I see it from that diagram. So I know you are an expert in this. So can you take us a little bit more deeply into the actual unit? So we saw the first picture, but please show us a little bit more about the components of it, please.
Yes. So let me briefly one more point to clarify. So I mean, two compressors can be used on the cathode side, but in addition also on the anode side. So for instance, for hydrogen recirculation dedicated for these designs, or for electrolyzer hydrogen recirculation.
So you also could use a turbo compressor for recirculating the hydrogen.
So if you're going to run a turbo compressor, what can we say about turbo compressors? First of all, they run continuously and are not positive displacement. It's unlikely that they reach high pressures. The airflow, and for that matter, the gas flow, can be achieved by how many different pumps do you want? One motor and three different. So is that what he's saying? Can you install those different designs in different? Looks to me like that's a component that is sort of like full size, and you put one in line, and you don't put three in line. They look like they're powered by about 12 volts. Maybe
AI
that's
can help
the point.
employees deal with onboarding, benefits, and other busy work so they can actually do the work
What
they
a
love.
nonsense. Why have we got to have
Dad's
this in the
loving
middle of
it. He's in
this?
the zone right now.
Can't hardly be in the zone.
When Idris Elba walks into your office, I know. It's a lot.
Exactly.
Hello, my name is Steven. Welcome to HyFind and Tech Talks, where we understand the technology that makes the hydrogen economy
We've
work.
jumped on to
Today,
H2
I'm very
refueling
pleased to
now.
welcome Jan Andreas of Anleg. He has spent the last
So try and go back. We're going to go back to Google Ad Services. Hydrogen tank systems previous.
Velocity,
Right.
the collective flow towards the end application, which could, for instance, be a fuel cell stack.
Yeah.
And maybe on the right-hand side, you can see one of our more recent designs that we have already presented at numerous fairs, where we can see actually how it looks in real life, which is a cut through of our one of our CAD designs. So maybe I can also show you how typically like what is the variation of such impeller designs, which is from my perspective very interesting to see. As you can see, there's a huge variety. So-called mixed flow designs where we have also a radial component, or the classical design which one would see in fuel cell stack applications.
So what is the difference between one that let's say narrows up and one that's completely what's the main difference?
So the main difference is directed. It's a very technical question actually.
Static head, is that what he
The
said?
difference is directed to the flow coefficient. So essentially the throughput that such a compressor needs to be able to be designed for. For instance, once we go towards axial flow designs, which is a classic for gas turbine designs, for instance, we have high mass flows requirements. Whereas when we go to really radial designs, which is for instance a purely radial design, 2D even, we have very low mass flows.
Right. Okay. So the mass flow essentially makes a difference. Okay.
Correct.
Well, so you have already mentioned some applications.
What does he mean, the mass flow makes a difference? Of course the mass flow makes a difference.
I mean, there are
Absurd comment.
three main applications actually, and also actually for that purpose I also brought you another image that I could show you, which is a very simplified schematic of a proton exchange membrane fuel cell. So piping diagrams essentially, where we can see the air inlet, and here we have our air compressor. It's one of the main application areas for these turbo compressors, compressing the air, generating for the cathode side to produce the air, or eventually the oxygen that is required by these fuel cell stacks.
Oh yeah. So we see that it pushes the air into the humidifier and then into the system, and it needs also cooling, as I see it from that diagram. So I know you are an expert in this. So can you take us a little bit more deeply into the actual unit? So we saw the first picture, but please show us
See
a
the
little bit more
same
about the components,
formulaic
please.
with every interview he does.
Let me briefly one more point to clarify. So I mean, two compressors can be used on the cathode side, but in addition also on the anode side. So for instance, for hydrogen recirculation dedicated for these designs, or for electrolyzer hydrogen recirculation.
So you also could use a turbo compressor for recirculating the hydrogen on
Absolutely.
on the okay.
Absolutely.
And also for in electrolyzer.
Dedicated designs though.
Yes.
But my business unit is really focusing on the air path, so on the cathode side. But generally speaking, turbo compressors can also be used for hydrogen recirculation purposes.
Understood.
So back to the original question.
He always
yours.
says understood, like there isn't anything more to understand.
Of how such a compressor system looks
Really
like.
annoys
What I
me.
brought here is actually a cut through of one of our compressor systems. So first I'm going to zoom out a bit. So in the beginning I only talked about the aerodynamics, which is only a portion. Obviously it's an important part, but it's only a portion of what the compressor system is consisting of. So on the left hand side we can see the compressor, and on the right hand side we can see the converter. So maybe let's go from left to right. So I already explained to you the impeller and the aerodynamics, and the impeller is usually connected to a rotor, which rotates at a high rotational speed. The rotor itself is suspended by so-called gas bearings, which makes this entire thing special. Why does it make it special? Because it's generating compressed air, which is oil-free and particle-free, and virtually nowhere. That's the second bit. Then obviously the torque needs to be generated to compress this air, right? And the torque is generated by an electric motor. In this particular case, we can see it's mounted around or in between the two radial bearings, which is our stator winding. And in the middle, we have our magnet, so a permanent magnet arrangement.
Yes.
So we are talking about permanent magnet synchronous machines that we use here, which are specially designed for high rotational speeds, where we have to take into account a couple of intricate things in the design process.
So the magnets.
Yes.
So actually, you mentioned high rotational speed. So I'm just trying to imagine being at the impeller. So that gets up to a very high RPM stage, and you also mentioned some really fast speeds there. I mean, doesn't this, don't you reach the sound barrier there and things like that? Don't you get into other kind of physical problems because of this?
So maybe to give you a couple of values here, which might be interesting for the view as well. So we range between rotational speeds of so for the larger compressor around 120 kilo RPM, so 120,000 RPM, up to 300,000 RPM for the smaller systems. Usually, which means when we convert that into velocities, we're talking about 300 to 400 meters a second.
Wow.
So generally speaking, sound barrier is something we try to avoid because supersonic operation always results in shocks.
Yeah.
So compressibility effects, shocks always are associated with irreversible processes, and ultimately also in a reduction in efficiency.
Okay, understood.
So thus, we are trying not to operate in supersonic machine.
And I see there was cooling. I saw from diagram. So what is actually being cooled is the electric motor. That's what's being cooled. So not.
So obviously within that system, we have a couple of sources for losses.
Yes.
One is, for instance, the gas bearings that generate losses.
Yes.
But mainly it is the electric motor, as you indicate.
Yes.
And where we either can cool it with water or with a cooling medium, or it is air cooled.
Okay. I'm very curious about the gas bearings, Markus. Maybe you can tell us a little bit more about that, because I know you also have a bit of a specialty around that. Firstly, I want to ask, how does it work? And also, I mean, if it's a compressor, it actually has one chamber where there's air. So isn't that an interaction with the actual medium that is being pumped?
So we have the same medium in there, obviously.
Yeah.
So I have to check whether I have a slide that I could show you. Yes, here we go. So let's dive into the details of gas bearings. I mean, gas bearings are very interesting. Generally speaking, one can differentiate between hydrostatic and hydrodynamic bearings for mobility applications, which is the most current case, for instance, for road applications or aerospace applications. Hydrodynamic bearings is the one that one uses. Reason being, simplified design, few external parts, and so on. How does it work? One has essentially a shaft, and then one has a bushing, and through rotation, one generates a pressure through the rotation within the small gaps between the journal and the bushing, which generates a cushion where the journal floats on top. That's essentially how it works.
So
fundamentally.
So by spinning the fluid around or in the gap of these two, you create a cushion that is strong enough for that to carry. Okay.
Correct. Exactly. I mean, I can maybe briefly show you. I mean, there are different types of gas bearings one could, for instance, use. The simplest one can think of is a plain bearing, where essentially it just has a cylinder and a bushing, which is a pipe, so to speak. And just by rotation and the co-ed flow, one generates a cushion where the road starts floating. Strongly and narrow regime where one can operate these bearings. And for instance, the technology that we mostly use is herringbone grooved bearings, where we can engrave structures to increase the regime where these systems can operate.
Okay, and when you have this kind of thing, like I said, if it's a pressure chamber on one side where it's spinning essentially, do you see any effect of the air? In this case, you're moving air, but do you see any effect of that in the bearing when the pressure rises in the spinning?
No, not particularly. There's no direct interaction.
Oh, there is no. Okay. Okay. Yeah, and so essentially this floats then, and just using the
watts per
opportunity
cubic meter.
What
Why is
happens
nobody
when,
talking
the
about
compressor shakes or gets shocks and
watts
so on?
per
Because I mean, obviously, if it's a physical
game ramp
bearing,
up?
let me just call it that.
Information
bearing,
like
so
this
everyone knows,
is
okay, there is
required,
something.
not.
But here now we are floating on a cushion. How does that work?
We don't want to generalize
What is,
discussion about air
actually, when I
bearings,
talk
do
to other
we?
engineers, it's always surprising to them that these gas bearing type of bearing, I mean, I can briefly show you another image. They actually have stiffnesses which are comparable to ball bearings, which is for some people very surprising. Which means, how does it work? So by rotation, we have this gas film where the journal is floating, and once we have a vibration shock, so it's essentially displacement, on one side we decrease the gap of this gas film, which increases the stiffness of the gas film, thereby exerting a force on the journal in the opposite direction, which means there is always a force acting into the centering of the journal when we have an external force acting, and it's such as
we
vibration
understand
or shock.
this.
Here on the right-hand side, you can see actually one of our compressors being tested on a vibrational bench where we, for instance, test the systems up to 20 G under real conditions.
So, okay, so this is clear. The shock perspective. Okay, that's very, very interesting. That is that kind of resistance. What about load bearing? Sorry if I asked, but so what if it's a very heavy shaft or something? These air bearings fine for that as well?
Absolutely. You have to obviously you need to design for it. Yes.
Yes.
The size increases, and there needs to be obviously attention to how you design such a bearing. But in terms of forces, you can definitely design also for larger shafts. I mean, for instance, here we tested up to 20 G acceleration, which means the forces of this rotor under acceleration is quite large.
Okay, and last question for the air bearings. What speed does it have to actually start working? Because I was just going through my head like, it could be used in other application mode. It does need to have a certain speed, right, before it starts working?
Yes, I can briefly elaborate on that as well. And actually, that's a very common question, which is why I also wrote an image.
It doesn't ramp back.
Typically speaking, when we look at curves, when we actually accelerate and increase the speed of such gas bearing type bearings, we have a mixed regime where essentially the rotor is still not yet floating, and we have a certain lift-off speed, which is at a very low rotational speed compared to the maximum.
Yes.
And after that, essentially the rotor floats and has virtually no contact anymore.
Okay. Wow. Okay. Well, no contact. That sounds like easy maintenance and these kind of things. Which brings me to another question, Marcus. I know that the compressors are often like maybe one of the cost drivers in the whole, especially fuel cell systems. Can you elaborate a little bit on that? Like, why or what is it that's so expensive on a turbo compressor like this?
So maybe I can give you a little bit of an insight into how much value is also given by such a compressor. Let me briefly show you one of the images here. So for an entire fuel cell system, component share value for the air compressor is up to 20% when we talk about the entire fuel cell system, which also, furthermore, not only the value that is created by the compressor, but also
is 50%, see?
The power consumption is also 10 to 20% of the entire system, which also is a strong argument why these compressor systems are worth to further develop
but really, he should identify the three sources
a substantial part of the fuel cell system, which is what I'm trying to say.
Okay, so that means you guys are working on getting them even better, hopefully bringing down the cost as well. Can you give us a bit of an outlook on?
Oh, come on! That's just give the lad a break. I mean. Presentation format does not allow for the innovator to express their product innovation in such a way that it can be adopted by other. I mean, in a way, what he's basically saying is you've got to compress the hydrogen that you're producing, or compress the hydrogen that you want to burn. And in another place you want to rarefy the oxygen or concentrate the oxygen. You do not want to develop a pressure differential across the membrane unless you're consciously aware of the fact that you are deliberately manufacturing cathode and anode in respect of the OR and the HRR. That's the way to start it. The model fundamentally revolves around HRR and ORR. And the two processes are different, and one is exothermic and the other is endothermic. So in a sense you've got to store the heat as well. Oh dear. A lot of thought to be put into this. But if I was to just conclude with what Copilot had to say. Didn't get to it, did I? Sorry. Earlier session. I think that's one of the rubbish things about Copilot these days. It doesn't save the session, does it? Is that right? Oh, we seem to have gone right into some kind of mode now. Come on, Copilot. Trying to connect. Poor network connection. Forget it for tonight. Oh, here we go. Earlier conversation, please, Copilot. I want your earlier conversation, not what type of workout is intended to increase my flexibility. Our earlier conversation. Yeah, forget it.